with their hair down low. Okay, so we are looking at Chapter 9, the end of Chapter 9. The last time I'll do these problems for you guys because it's the end of the semester. All right, so first up, Chapter 9, problem 26, then 2830. Okay. So problem 26. A 1-to-1 mixture of helium, red, and argon, blue, at 300 Kelvin is portrayed on the left. Draw the same mixture when the temperature is lowered to 150 Kelvin. It's going to look exactly the same. This is a static shot, therefore you cannot tell the difference between the two pictures. The only difference between 300 Kelvin and 150 Kelvin is that the particles are moving faster at 350 than they are at, that they're moving faster at 300 than they are at 150. Seriously, that's it. So it's going to look exactly the same. 1, 2, 3, 4, 5, 6, 7 of each colored dot. All right, 28. Assume that you have a sample of gas in a cylinder with a movable piston, as shown in the following diagram, shown below. Redraw the apparatus to show what the sample will look like after A, the temperature is increased from 300 Kelvin to 450 Kelvin at constant pressure. Okay, so that's easy enough. This time there's actually something to show. Nope, it's not times 2. It's times 1.5. Okay. So if you increase the pressure from 300 Kelvin to 450 Kelvin, that's 1.5 times the temperature. Did I say we're increasing the temperature? So that's 1.5 times the temperature. Therefore, it's going to be 1.5 times the volume. The volume is going to increase. All right, B, the pressure is increased from 1 atmospheres to 2 atmospheres at constant temperature. All right, so if you double the pressure, which is what we're doing here, then you're going to cut the volume in half. And finally, C, the temperature is decreased from 300 Kelvin to 200 Kelvin, and the pressure is decreased from 3 atmospheres to 2 atmospheres. Now, the thing is, pressure, temperature, volume, these are all state functions, so you can do these each one at a time in whatever order you want. So first, let's do temp. So if you decrease the temperature from 300 to 200, the volume is going to go down to 2/3. 300 to 200, you're going down to 2/3 temperature, so you're going to go down to 2/3 the volume. But then, second step, pressure. You're decreasing the pressure, so the volume is going to increase. And you're going from 3 atmospheres to 2 atmospheres. Therefore, you're going to go back up to 3/2 of volume 2. Meaning that volume 3 is equal to volume 1. Okay. The pressure change and the temperature change are acting in opposite directions. And they're acting in opposite directions in the exact same quantity. And 30. Assume that you have a mixture of helium and xenon at 300 Kelvin. Which of the drawings best represents the mixture Well, I mean, if they're mixed, then they're going to be mixed. Then they're not going to be in separate halves of the container. That's just not going to happen. I mean, it could happen temporarily in very unlikely circumstances, but otherwise they're just going to be all jumbled together. See, A and B are very low entropy conditions. C is the high entropy condition, where everything is all jumbled. That's a weird question. All right, next up. 36 and 38. What is temperature a measure of? Okay, temperature is a measure of the average kinetic energy of all the particles of a system. Average. Average is important there. 38. Atmospheric pressure at the top of Pikes Peak in Colorado is approximately 480 millimeters mercury. That's pretty darn low. Convert this value to atmospheres and to pascals. Okay, so it's 480, so I'm going to need both this guy and this guy. Okay. So 480 millimeters mercury, there we go, times 1 atmosphere for every 760 millimeters mercury is equal to 0.63. I'm just going to go ahead and call it 2 atmospheres. Yeah, very low. That's probably above the edema range, the place where, people can no longer survive. All right, and then we convert that to pascals by multiplying by 101,325 pascals per atmosphere. Means we're looking at 64,000 pascals. Or 0.64 bar. Just for giggles. Okay, who is next? 44, 46, 48, 50, 52, 54, 56, 58. So we're going to do 44 through 58. I don't know why I have that goddamn song stuck in my head. Okay, so 44. Calculate the average molecular weight of air from the data given in table 9.1. Going to page... Oh, wow. The average molecular weight of air. Okay, so what we're going to do is we're going to take the molecular weight of each of our substances, multiply it by the percent by mass. Easy peasy. This is going to take a full sheet of paper, though. Okay. So we have nitrogen, oxygen, argon, carbon dioxide. We can stop there. The others are so insignificant. 0.00127%. Yeah, I'm just going to go ahead and stop there. The others are not going to contribute. So let's see, that's 75.52, 23.14, 1.29, and 0.060. 28.014, 31.998. I do not know the molar mass of argon. Argon, 39.948. And CO2, you'd think I'd have that one memorized by now. All right, so... Ooh, no. 0.014. So nitrogen is going to contribute 21.15. No, 16. Oxygen contributes 7.40. Argon, I'm just multiplying each one's percentage by the molar mass. So that's 5.2. And carbon dioxide. And you can see why I went ahead and just decided to ignore all of the others. If they do make a difference, it will not be very large. So the average molar mass of the atmosphere is 29.11. But just in case, what happened? Did I? Yes, I did. I just replaced that page. Okay. Let's. Okay. Where are we? We were on problem 44, was it? Yes. Okay, so let's go ahead to probably A14. No. Oh, I'm thinking of A20. A1. Okay. I obviously do not have this memorized. Answers to selected problems. A22. So let's skip ahead a few pages. Not quite far enough. Too far. Just right. 944, 28.96. Where did I screw up, I wonder? Okay, so we're going back to page 317. Where did I get... Oh, no, that's all correct. Did I screw? I must have screwed up in the calculator, is what I must have done. So let's see. 28.014 times 75.52% plus 31.998 times 0.2314%, 23.14% plus 0.0129 times 39.948. And we're already above what they say. Yeah, I have no idea how they got that number. That's why I prefer it when they include how they worked things out. Weird. Yeah, well, I'm gonna roll with it. I'm gonna say they screwed up, not me. 342. Not quite. Close enough. Let's see. Boom. Okay. All right, 346. Assume that you have a cylinder with a movable piston. What would happen to the gas pressure inside the cylinder if you were to do the following? Triple the temperature while holding the volume constant. Well, you triple the temperature, you're going to triple the pressure. That's not one they told you, but it's one that you can work out knowing PVNERT. Let's go ahead and... There we go. So PVNERT, you can rearrange it like this. This lets you sort of recreate all the stuff. In this case, we're holding volume and moles constant. It's just P1 over T1 equals P2 over T2. So if you triple the temperature, you're going to triple the pressure. Okay. Reduce the amount of gas while holding the volume and temperature constant. So again, same relationship. P and moles, pressure and moles had the same sort of relationship as moles and volume did. So if you reduce the amount of gas by a third, you're going to reduce the pressure by a third. Decrease the volume at 45% at constant temperature. Okay, so I'm assuming that we have a constant amount of gas. It doesn't tell us that, but I'm assuming that we have constant gas in there. So that means that we're going to increase the pressure by 45%. Well, technically by something like 54.5454, I think. All right, halve the temperature and triple the volume. So if you halve the temperature, the pressure goes down by half. If you triple the volume or the pressure will go down by a third. So go down to 1/3, I should say. So the total change will be that the pressure goes down to 1/6 of what it was before. All right, 48. Which sample contains more molecules? 1 liter of oxygen at STP, 1 liter of air at STP, or 1 liter of hydrogen at STP? Well, it's not going to be air, because air contains things that aren't molecules. They're going to have the same number of moles of stuff, but some of the moles of air will include things like argon and helium. So that means that air will have fewer molecules, but oxygen and hydrogen would have equal numbers of molecules. I'm kind of doubting that. That they were intending to go quite that in depth. They probably mean you to say that they're all equal, but let's check. 37 is way too far. That's what I thought. It's 32. Yes. So 48. They all contain the same number. See, no, they contain the same number of particles, but not molecules. I'm smarter than they are. I'm a clever duck. All right, and 50. Oxygen gas is commonly sold in 49-liter steel containers at pressures of 150 atmospheres. What volume in liters would the gas occupy at a pressure of 1.02 atmospheres if its temperature remained unchanged? Okay, okay, so that first question is just P1V1 equals P2V2. So we know the initial. Okay, so we're looking for V2 is equal to P1V1 over P2. So the initial pressure is 49 point, no, that's the volume. Well, 49.0 liters times 150 atmospheres divided by 1.02 atmospheres. Uh, 49 times 150 divided by 1.02 is 7,206 liters. It would expand a lot. That's why you never try to breathe directly from a gas canister. If the temperature was raised from 20 to 35 degrees Celsius, ooh, that's a bad idea. But that's going from 293.15 Kelvin to we're going up by 15, so 308.15 Kelvin. So V2 is equal to V1 T2 over T1. So that's V1 over T1 equals V2 over T2. We're solving for volume 2. 49 times 308 divided by 293. Oops. 49 times 308 divided by 293. The 0.15 doesn't make too much of a difference here. It's going to be 51.5. It's not going to increase a heck of a lot, but it would be enough to put a strain on that cylinder, I'm telling you. All right, if 15 grams of CO2 gas, this is number 52, has a volume of 0.3 liters at 300 Kelvin, what is its pressure in millimeters of mercury? Oh. Okay, so this is a Pevner problem and a conversion problem. Okay, so P equals nRT over V. We need our moles, so 15.0 grams times 44.009 grams per mole. Oops. .3408 moles. So our pressure in atmospheres, 0.3408 times 0.08206 R, the universal gas constant, times, what was the 300 Kelvin, divided by our volume was 0.30. is 27.97 atmospheres times 760 millimeters of mercury per atmosphere. 21,300, let's call it, millimeters of mercury. Okay. So just a pavement problem and a Hujam-Thing problem. Problem 54. The matter in interstellar space consists almost entirely of hydrogen atoms in an atmosphere at a temperature of 100 Kelvin and a density of approximately 1 atom per cubic centimeter. What is the gas pressure in millimeters of mercury? Okay. 1 atom per cubic centimeter. Okay. So I'm going to convert from atoms per cubic centimeter to moles per liter. 1 atom per 1 cubic centimeter. So a liter is a cubic decimeter. 1 centimeter, 1 decimeter. Okay, so there are 1 decimeter is equal to 10 centimeters. Yes. Yes, good. And so we'd cube that. But we also have to divide by Avogadro's number to get moles. Yep. Okay, so oops, why are you? Okay, that's my bad. 1,000 divided by 6.022 times 10 to the 23rd gives us 1.661 times 10 to the negative 21st moles per liter, aka N divided by V. Okay, so when we plug this into pVNERT, you'll see P equals nRT over V. And we already have the N over V part, so we can just multiply this. You can't see what I'm writing. Okay, so what I did here, step by step, we have 1 atom per cubic centimeter. There are 10 centimeters in a decimeter. So we cube that, and we convert cubic centimeters to cubic decimeters, where 1 liter is equal to 1 cubic decimeter. So you multiply by 1,000, and you've converted to liters. The other thing I did was I converted from atoms to moles using Avogadro's number. There are 6.022 times 10 to the 23rd atoms in a mole, so you divide by Avogadro's number, and you get your answer, 1.661 times 10 to the negative 21st moles per liter. Okay, or that is N over V. So we multiply that by RT, and we'll get the pressure in atmospheres. Just to prove that, liter atmospheres per mole Kelvin times, it was 100 Kelvin. Okay. Yeah, did they say 100? Problem 54, yes, okay. So when we do this, moles cancels, liters cancel, and Kelvin cancels, leaving us with atmospheres. So we go ahead and plug those numbers in over here. Times 0.08206 times 100 is 1.363 times 10 to the negative 20th atmospheres. But they wanted it in millimeters of mercury, so times 760 millimeters of mercury per atmosphere. Still going to be really low. 1.036 times 10 to the negative 17th millimeters of mercury. In space, no one can hear you scream because the gas is too attenuated. All right. Many laboratory gases are sold in steel cylinders with a volume of 43.8 liters. What mass in grams of argon is inside a cylinder whose pressure is 17,180 kilopascals at 20 degrees Celsius? Okay. So once again, we're doing some conversions. So 17,180 kilopascals times 1 atmosphere per every 101.325 kilopascals. Okay, a kilopascal is 1,000 pascals. A pascal, 101,325 pascals is 101.325 kilopascals. So our pressure is 17,180 divided by 101.325 is 169.6 atmospheres. All right, the other thing we need to do is we need to convert temperature. Yes, so 20 degrees Celsius is 293.15 Kelvin. Is that everything? Yeah, okay. So we're looking for N. N equals PV over RT. So we have 169.6 atmospheres times 43.8 liters divided by 0.08206 liter atmospheres per mole Kelvin times 293.15 Kelvin. Divide by R, now divide by temperature. Gets us 308.8 moles. And then we multiply that by 39.095 times, dang it, 308.8. So that gets us 12,072 grams, or 12,073, or, oops, 39.095 grams per mole is equal to 12,070 grams, or 12.07 kilograms, which isn't all that much. I mean, it's about 25 pounds. And given that we're talking about a thick-walled steel cylinder, the cylinder weighs a lot more than the gas inside it. I think that was the last of that series. Nope, we have one more. Problem 58 comes next. What sample contains more molecules, 15 liters of steam at 123 Celsius and 0.93 atmospheres, or 10.5 grams of ice at -5 degrees Celsius? Okay, the temperature for the ice is only so that we can confirm that it's, ice. But 10.5 grams of ice, you're just going to convert that using the molar mass. So 10.5 divided by 18.02 grams per mole gets you 0.583 moles of ice. And as for the steam, they gave us liters, degrees Celsius, and atmospheres. They did not give us a mass or anything like that, so we're going to have to use PV for that one. But N equals PV over RT is equal to 0.93 times 15.0 divided by 0.08206 and 123. It's going to be 398 Kelvin. Okay, so that's 0.427 moles of steam. And you don't need to convert to molecules. Whichever one has more moles will have more molecules, which means that the ice has more molecules of water because there's just more moles of ice. All right, now we're done with that series. 62 and 64. 62. What is the total mass in grams of oxygen in a room measuring 4 meters by 5 meters by 2.5 meters? Assume the gas is at STP and that air contains 0.2095% oxygen by volume. Okay, so let's just go ahead and find the total volume. The total volume is going to be 4 by 5 by 2.5. So we're looking at 50 cubic meters. I believe, well, let's go ahead and multiply by 1 decimeter per meter. How many decimeters are there in a meter? It's going to be 10. We cube that, and that means that it's 50,000 liters for the whole room, but only 0.2095. Okay, so 20.95% of that volume is oxygen. So we just times 0.2095. It's going to be a little bit more than 5,000 liters of oxygen. Or no, sorry, 10,000 liters, because it's about 1/5. Times 0.2095, because it's 20.95% volume. So 20.95% of that volume is oxygen. So 10,475 liters. Of oxygen. Okay, so now we can plug that into PVnert. They're asking for mass eventually. But N equals PV over RT. That's standard temperature and pressure, so 1 atmosphere times 10,475 liters divided by 0.08206 times 298.15. 20 degrees or 25 degrees? How do they define STP? Dang it. Oh, what am I doing? I could just do this. Bop on over to here. Do they define STP here? Somewhere around here they must. No, they define that in Chapter 8 somewhere. $25 degrees. Okay, so it's 298. Excellent. Okay. Okay, so bring our calculator back up. 10,475 liters divided by 0.082. 0.08206. And then we divide by 298.15. Gives us 428.1 moles of oxygen. Then we multiply that by the molar mass of oxygen. 13.700 kilograms. Wow, sorry, it's 13,700 grams, which is what they actually asked for. It's 13.7 kilograms. Okay. And that's just in a normal-sized room. All right, so that was 62. Yes, now 64. 1 mole of an ideal gas has a volume of 22.414 liters at STP. Assuming ideal gas behavior, what are the densities of the following gases in grams per liter at STP? 1 mole. Okay, so what is the molar mass of ammonia? Then we divide that by 22.414. What's the molar mass of CO2? Divide that by 22.414. This problem is a little bit easier than they are saying. So, for ammonia, 12.011 plus 1.0079 times 4 oh, no, 12.011 plus 1.0079 times 4 divided by 22.414. So for methane, it is 26.45 grams per liter. No, it's not. Where the hell did that come from? What the heck is going on? This calculator is screwing with me. 16.043 divided by 22.414. 0.716 grams per liter. Good Lord. For CO2, it's going to be 44.009 divided by 22.414. 1.963 grams per liter. And for O2, it's 31.998 divided by 22.414. Measuring density was actually the way they found molar masses once upon a time. 1.428 grams per liter. Okay. What was next? I think it's 68. 68, 70. Yep. Pure oxygen gas was first prepared by heating mercury to oxide. What volume a liter of oxygen at STP is released by heating 10.57 grams of mercury to oxide? All right, so that is a 1 to 2 ratio. So we're going to have to convert to we're going to have to convert from grams of the mercury to oxide to moles, then to moles of oxygen, then we can plug that into PVNERT. So 10.057 grams of mercury oxide. Need the molar mass, which means I need to bring out the periodic table. Mercury is 200.59. Plus 31.998. Okay, that one was all me. So 232.588 grams per mole times 1 mole O2 for every 2 moles of HGO. Okay, and that'll get us our moles of oxygen that we're plugging into PVNERT. So 0.5 divided by 232.588 divided by 2. 0.02272 moles of oxygen. And it's at STP? Yeah, you know me. Okay. So volume equals nRT over P. 0.02272 times 0.08206 times 298 divided by 1. It would help if I had my calculator up. 0.02272 times 0.08206 times 298. 0.5556 liters. Hydrogen gas can be prepared by the reaction of zinc metal with aqueous hydrochloric acid. How many liters of H2 would be formed at 742 millimeters mercury and 15 degrees Celsius if the 25.5 grams of zinc was allowed to react? All right, so it's not an limiting reactant problem. At least there's that. Still, just a bog standard stoic. All right. So 25.5 grams of zinc. It's going to be a 1-to-1 ratio. So once we get the molar mass of our zinc, 65.38. So that's 0.39 moles of zinc is 0.390 moles of hydrogen. And 742 millimeters of mercury. Let's go ahead and convert that real quick. 740 divided by 706. 740 divided by 760. I swear this just must have a really bad connection. Given that my keyboard is further away than usual, that might actually be the case. Okay. So we're looking at 0.974 atmospheres. And 15 degrees Celsius is going to be 273, 288 Kelvin. Okay, so V equals nRT over P. 0.390 times 0.08206 times 288 divided by 0.974. Why am I divided by 0.296? What did I do? 0.39, 0.08, okay. Okay, okay. 9.46 liters. Wow, I just totally spaced out in the middle of what I was doing there. Okay, just double checking. Yes, okay, so it's going to be 9.46 liters of hydrogen. How many grams of zinc would you start with if you wanted to prepare 5 liters at 350 millimeters mercury and 30 degrees Celsius? Okay, so same deal, other direction. N equals PV over RT. Pressure, let's see, it's 350 millimeters of mercury. 0.461 atmospheres. Our volume is 5 liters, 0.08206, 303 Kelvin. Yes. Zero 0.0927 moles of hydrogen is going to be 0.0927 moles of zinc because it is 1-to-1 between hydrogen and zinc. So now we multiply that by the molar mass of zinc, which I have already forgotten, 65.38. .06 grams. So just regular stoic. It's just another way to go back and forth between moles. That was 68 and 70. All right, now 80, 82, 84, 86. 80 through 86. A mixture of 14.2 grams of hydrogen, 36.7 grams of argon is placed in a 100-liter container at 290 Kelvin. And then they just ask us to calculate the partial pressure of each. So we just need to find the moles of each and then plug those into 2 separate P-Vnert equations. That's kind of fatuous. I mean, that's not even a partial pressure problem, really. All right, so 14.2 grams of hydrogen, 2.0158 grams per mole. .044 moles. P equals nRT over V, so 7.044 times 0.08206 times 290 Kelvin divided by 100 liters. 1.67 atmospheres. For argon, it's going to be a little bit less. 36.7 grams times 39.95. Zero 0.919 moles of argon. So it's going to be 0.919 times all that stuff. Zero 0.219 atmospheres. '82. A sample of magnesium metal reacts with aqueous HCl to yield hydrogen gas. The gas that forms is found to have a volume of 3.557 liters at 25 degrees Celsius and a pressure of 747 millimeters mercury. Assuming the gas is saturated with water vapor at a partial pressure of 23.8 millimeters mercury, what is the partial pressure in millimeters of mercury of the hydrogen? How many grams of magnesium metal were used in the reaction? Obviously, we're assuming a 100% yield. So, the partial pressure of the hydrogen is going to be 747 millimeters of mercury minus the water, which was 23.8 millimeters of mercury. So the pressure of the hydrogen is 723.2. So we convert that to atmospheres. Divide by 760, that'll give us 0.952 atmospheres. So the moles of mercury is PV over RT, not mercury, the moles of hydrogen. 0.952 times 3.557, I believe. Yes. 0.08206, and what was the 298? 25 degrees Celsius is 298 Kelvin, roughly. .138 moles of hydrogen. And so they're asking how many grams of magnesium. It's a 1-to-1 ratio between hydrogen and magnesium. So it's 0.138 moles of magnesium. Just the same. All right, so that means that now we just need to multiply by the molar mass of magnesium, 24.30 grams per mole. .365 grams. Little fur. What are the basic assumptions of the kinetic molecular theory? Postulate the first. All gases are made of particles in constant random motion. Postulate 2. No, I do know these off the top of my head. Let's see. Postulate 2. Oh, the volume of the particles is negligible compared to the volume of the gas as a whole. Postulate 3. The particles do not interact except to collide. Postulate 4. The collisions are perfectly elastic. And Postulate 5. Temperature is a measure of the average kinetic energy of the particles of the gas. Boom. What is the difference between heat and temperature? Heat is the transfer of thermal energy from one location to another. Temperature is a measure of the average random kinetic energy of the particles of a substance. I'm on top of my game because I've been doing this for quite a long time. Okay. 90. Which has a higher average speed? Hydrogen at 150 Kelvin or helium at 375 degrees Celsius? Ooh, that's a good question. Temperature is, or sorry, temperature. Hydrogen will have a higher a higher average speed at the same temperature, but they're not at the same temperature. So H2 equals, let's see, it has half the mass, so it's going to be 1.4 times as fast. But helium is going to be 375 plus 298, or sorry, plus 273. That's 648. 648 over 150. That's going to be 4 point something. 4 and a third, I think. Yeah. So, by mass, hydrogen has a 1.4 times advantage, but by temperature, helium has a 4.32 times advantage. So, to put it another way, the increased temperature of the helium outweighs the decreased mass of the hydrogen. Oh, wait, I forgot to take the square root. 2 something. So call it 2.1. It's going to be a little bit less than 2.1. Still, I have a calculator right here. What am I doing? 2.06. It's still, it's 2.08. You know, that's still, that's still a better, the higher temperature of the helium still outweighs it. I forgot the square root, and that could have been a deal breaker. The 1.4 here comes because hydrogen weighs twice as much as helium. Sorry, helium weighs twice as much as hydrogen. Therefore, hydrogen is the square root of 2, or 1.4, times as fast as helium. The helium, though, is at 4.32 times the temperature of the hydrogen, so that gives it a 2.1-ish times advantage. The 2.1 is greater than the 1.4. Helium moves faster. Next up is 102. The surface temperature of Venus is about 1050 Kelvin, and the pressure is about 75 Earth atmospheres. Assuming that these conditions represent a Venusian STP, what is the standard molar volume in liters of a gas on Venus? Okay. So we have temperature and we have pressure. We are looking for moles per liter. Okay. So PV equals nRT. N over V equals P over RT. Yes. All right, so we have 75 atmospheres, and we have 0.08, 206, and 1050 Kelvin. So instead of being 22.414 liters per mole, yeah, I was about to go moles per liter. We don't want this. We want V over N equals RT over P, because we're looking for liters per mole instead of moles per liter. Okay, so 0.08206 times 1050 divided by 75. Is 1.15 liters per mole, compared to the 22.414 liters per mole that we have here on Earth. (104, 108, 110, 118). That's a cough. Excuse me. Uranium hexafluoride, a molecular solid used for purification of the uranium isotope needed to fuel nuclear power plants, sublimes at 56.5 degrees Celsius. Assume that you have a 22.9 liter vessel that contains 512.9 grams of uranium hexafluoride at 70 degrees Celsius. What is the pressure of the vessel calculated using the ideal gas law? Okay. So first we're going to need the molar mass of uranium hexafluoride, which means I need the periodic table. All right, uranium is down here, 238.03. And then our fluorine, 18.998. Molar mass is 352.018 grams per mole for our uranium hexafluoride. So we have 512.9 grams. .457 moles. So now we plug that into PVNERT. Oh wait, 70 degrees Celsius is going to be 343 Kelvin. Yep, okay. So pressure is equal to nRT over V, 1.457 moles times 0.08206 times 343 Kelvin divided by 22.9 liters. .79 atmospheres. All right, so that's the ideal gas law. What is the pressure in the vessel calculated using the Van der Waals equation? Okay, let's go ahead. I'm going to have to go back and... Okay, so A is 15.80. B is 0.1128. Now I'm going to have to go back because I don't have the Van der Waals equation memorized. Why would I? We never use it. Okay, so we're looking for pressure. P is equal to nRT over V minus NB minus AN squared over V squared. 1.457 times 0.08206 times 343 divided by 22.9 minus 1.457 times 0.1128. Okay, so this corrects for the fact that the particles actually do take up space. That's what NB is for. Minus 18.8 times 1.457 divided by 1.457 squared divided by 22.9 squared. Yes, and the number of moles squared divided by the volume squared multiplied by A, that's all to take into account the interactions. The squaring comes because A interacts with B and B interacts with, molecule A interacts with molecule B, and at the same time, molecule B interacts with molecule A. So it's, yeah. Clear everything, and parentheses. 1.457 times 0.08206 times 343 divided by, parentheses, 22.9 minus 1.457 times 0.1128, close parentheses, minus, open parentheses, 15.8 times 1.457 squared divided by 22.9 squared, close parentheses, equals 1.74 atmospheres. So it's not an insignificant difference. That's about a 2-3% difference between the ideal gas and the real gas. So notice that this isn't a particularly hot gas. 70 degrees Celsius would be very hot for us. We wouldn't really survive well at that temperature. That's very hot. Human body temperature is about 34 degrees Celsius. It would be very hideously uncomfortable. Nevertheless, it's not a particularly high temperature. This is a fairly low pressure, though. So it's not a huge deviation. All right. Next up. 110, or is it 108? 108, 110, 118. Pakistan's K2 is the world's second tallest mountain, with an altitude of 28,251 feet. Its base camp, where climbers stop to acclimate, is located about 16,400 feet above sea level. Approximate atmospheric pressure, P, at different altitudes is given by the equation P is equal to E to the negative h over 7,000, where P is in atmospheres and h is the altitude in meters. What is the approximate atmospheric pressure in millimeters of mercury at K2 base camp? I hate you so much. All right. One foot is 0.3048 meters. So, 0.3048 meters per foot times 16,400 feet. I watched a movie called K2 once when I was a kid. I remember nothing about it. So, 4,000, it's 5,000 meters. Okay, so atmospheric pressure is going to be to the negative 5,000 over 7,000. So the pressure in atmospheres . 5 divided by 7 negative equals, and then where's E? To the negative 5/7. Okay. 0.4895 atmospheres times 760 millimeters mercury per atmosphere. 372 millimeters of mercury. What is the atmospheric pressure in millimeters of mercury at the summit? 0.3048 times 28,251 feet divided by 7,000, 1.230. E So the atmospheric pressure in millimeters of mercury, so we have 0.2923 atmospheres is 222.1 millimeters of mercury. Very low, very low. Definitely at the death zone. Assuming the mole fraction of oxygen in the air is 0.2095, what is the partial pressure in oxygen at the summit? Just multiply by 0.2095. That's all. 46.54 millimeters of mercury. Very low. Very low. 110. Assuming that you take a flask, evacuate it to remove all the air, and find its mass to be 478.1 grams, you then fill it with argon to a pressure of 2.15 atmospheres and reweigh it. What would the balance read in grams if the flask has a volume of 7.35 liters and the temperature is 20 degrees Celsius? Okay, so they're not doing a heck of a lot there. This is just a PNUT problem that is pretending to be fancy. N equals PV over RT equals 2.15 times 7.35 divided by 0.08, 206 times 293 will give us the moles of argon. Zero 0.657 moles. And then we're going to multiply that by 39.95 grams per mole. Gives us 26.26 grams of argon, which we then add to the mass of the flask, which was 478.1. The new mass will read 504.4 grams. And 118. Natural gas is a mixture of hydrocarbons, primarily methane and ethane. A typical mixture might have 0.915 of methane and 0.085 of ethane. Let's assume that we have a 15.5 gram sample of natural gas and a volume of 15 liters at a temperature of 20 degrees Celsius. How many total moles of gas are in the sample? Whew. Okay. That is slightly difficult. Okay, so 0.915 times what am I looking for? What am I looking for? The molar mass of methane. (16.04) times A plus 0.085 times the molar mass of ethane. (30.069 times 1 minus A) is equal to 15.50 grams. Now, what I'm doing here is I'm taking the mole fraction of methane, multiplying it by, hold on. I think I must be getting tired. Okay. Moles of methane times molar mass will get you grams of ethane. Moles of ethane times molar mass will get you grams of ethane. I am really having trouble working my way through this one. All right. Okay, so this one I'm confident of. Molar mass times moles of methane plus molar mass times moles of ethane is going to be 15.5. A plus B over C. No. A over A plus B is equal to 0.915. A is equal to 0.915 A plus 0.915 B. 0.915 B is equal to 0.085 A. B is equal to 0.085 divided by 0.915, 0.0929 A. I may be overthinking the hell out of this problem, but 16.043A plus 30.069 times 0.0929A is equal to 15.50. 30.069 times 0.0929 is 2.793A. 16.043. 18.836A is equal to 15.50. 15.5 divided by 18.836. A is equal to 0.823 moles of methane. Okay, so 16.043 times 0.823 means we have 13.20 grams of methane. And then 15.5 minus 13.2 leaves us with 2.30 grams of ethane. I'm going to go back and double check that those numbers work. 2.3 divided by 30.069 is 0.0765 moles of ethane. 0.823 divided by 0.823 plus 0.0765. 0.915. Okay, I did it. This is appropriate for the very end of the chapter. Okay, so we have 0.823 moles of methane, 0.0765 moles of ethane, which means the total moles of gas was 0.823 plus 0.0765, 0.9. Oh, man alive. 38? No, not 38. 34. Closer. Not quite right. Okay. 118. 118. 0.901. Yep, okay, good. All right, so now back to 350. 351. 352. Okay, what is the pressure of the sample in atmospheres? Okay. Our total is 0.9. I'm going to keep this rather closer to hand than that. So pressure is nRT over V is 0.9 times 0.08206 times 293 Kelvin divided by 15 liters. It's going to be somewhere between 1 and 2. 0.9 times 0.08206 times 293 divided by 15. 1.44 atmospheres. What is the partial pressure of each component in atmospheres? Okay, that's 0.823 times all of that, and 0.0765 times all of that. Or 1.44 times 0.915, 1.44 times 0.085. Partial pressure is equal to mole fraction times total pressure. 1.32 and 0.122. When the sample is burned in an excess of oxygen. I don't want to do this. I do not want to. To solve that, you need to look up the heat of combustion for methane and for ethane, and it's fairly straightforward. But I just don't want to go through the trouble of looking up the heats of combustion. It's just I would have to dig through half a dozen tables in a couple of different chapters, and I don't want to do it. Okay. And that is it. There are no more problems from the end of chapter problems for this guy. So that means that I am done for the evening, which means that this is the actual last video for the semester. Have a good one.